let's now look at the new skill review. It's just because sine and cosine and tangent, and they have some special relationship right here, so it gives rise to these special skill that we want to do. Let's learn to simplify. Right? So simplify a trig expression. So simplifying a trig expression. But let's say I'm going to bring in an example. So as a big topic right here, let's call that I'm going to call it example 1 right here. Right? So we want to simplify, right? Here's the idea. Let's say you have an expression about tangent of theta, okay? Then we multiply that with the cosine of theta, just something like that. You want to simplify. I mean, the expression itself looks pretty simplified already, right? The expression looks quite simple, right? But when it says simplify, that means potentially there's still way to make it even shorter, right? Even more simplified. So here's how I'm seeing it. To simplify this, the first thing, keep in mind, we already have that definition. Tangent is defined as what? So that expression equals what? Tangent is sine of theta over cosine theta. So we look at that. And we multiply with cosine theta. So it's just the exact expression, but I'm substituting tangent of theta by sine of theta divided by sine theta. We look at that so far. Okay. So now look at the good news for us. You see how it is a common factor in the cosine theta right now? So this is the cosine theta over 1, right? So we can cancel out the cosine theta factor completely. So look at how we have reduced this expression, how we have simplified this expression. Sine theta. It's even shorter than that. See what I mean? Okay. And so that's what it means by simplifying a trig expression like that. Right? Sometimes we can have, even though the expression has already looked pretty simple, but we can even further simplify it. Most of the time, I'm not saying all of the time, but most of the time, a big amount of time, we attempt to simplify something down to only contain sine or cosine. That's one of the big goals with that. But sometimes, I'm not saying that all the time. There are still exceptional cases out there where you still have to end up with some tangent or some cotangent involved. Okay, but a good amount of time. See, a good amount of time we want to simplify it down so that the final goal is just to have sine or cosine. See what I mean? Right. So you can call that part A here. And technically, by the end of this example, you already see what's going on. But let's do some more. Let's do some more so that you can get a better hang of it. Okay. So what about secant of theta? We want to simplify that. Secant of theta divided by tangent of theta. Okay. This should be our last one for today here. You see, secant theta is known as 1 over cosine theta. And then the denominator, tangent theta, is known to be sine theta over cosine theta. So in that way, right here, I can rewrite this. There's a fraction of 1 over cosine theta as numerator, so 1 over cosine theta. But I'm going to multiply to the denominator. Here we have another fraction, right? It's reciprocal. So that's cosine theta over sine theta. Okay. And so yes, just like that, simplifying means what? We're going to cancel away that common factor that appears at both top and bottom, right? So we reduce things down to a 1 over sine theta. So technically, in what I said earlier, see, a lot of time, a good amount of times, we're looking for a way to finally end up with a simpler expression involving either sine or cosine only. So we're there. Technically, we're there. But let me tell you guys this. You've learned that cosecant of theta equals 1 over sine of theta, right? So now you think about it, between these two choices over here, which expression looks simpler? The cosecant looks simpler, right? So this is some of the exceptional cases right here where even though we already arrive at some simplest form in terms of sine and cosine, but it's still simpler to rewrite all that as one simpler function. See what I'm saying now? Okay, so now we have a better choice of saying, you can just say, hey, the final answer in the simplest way of saying that cosecant theta. Okay? We have reduced that down to this. Right? So we've gone into some problems where we learn how to simplify a trig expression. Right? So now, along that way, I want to mention, let's take this as a remark here, something to pay attention to. Right? Now, when you're working with when you have seen enough trig functions and all that, right? Now these expressions right here, so when it says sine of theta, and then so the theta here is an indication of an angle. So in some other problems I may use a t, some other problems I may use an alpha or an x variable, basically. But so, I gotta make sure that you guys do not skip, okay? Do not skip the theta. Or when it comes to other variable, like people can use sine of x or sine of t or whatever, just don't skip that angle indication. So the same with cosine theta. Okay? And then you've also learned tangent theta. You've also learned cotangent theta. Right? So these variables here, they indicate the angles. And then there's secant theta. And then there's cosecant theta. So all of these, they come with an angle indicator. Okay? Don't skip these variables because think about it, skipping these, right? Skipping that, just a sine only, or just a cosine only, any of these, right, is meaningless. Right? Any expression like that is meaningless. So without an angle indication, right, you are just write a sign of sin, it means nothing. Okay, it doesn't have a meaning. So and the same with the cotangent, the tangent, and the secant, and the cosecant. So bottom line is never skip that sign again. The reason I really have to emphasize is because sooner or later, sometimes when we're in a rush situation, I've seen people in my past quarter making a mistake like this. And you guys especially at this point have done some simplification. So let's say when you're looking at so some of the problem we've done, let me take that simplification problem we've done from the last lecture right there, like the secant theta over tangent theta. And when people say, I was writing down the instruction that, hey, let's simplify this, right? I passed students in the past quarter doing this. They think that it's an SEC secant multiplied with theta. And then in the bottom, in the denominator, they think it was some TAN expression multiplied with theta. And so recognizing the common theta here, they cancel the theta and leaving that secant over tangent. See what I mean? Okay? And this is where it's a very logically incorrect step. Right? Because remember, these functions these expressions must always come with the angle. So it doesn't really mean multiplication. It doesn't mean SEC multiplied with theta. It doesn't mean SIN multiplied with theta. It's just one symbol that always has to come. So if you skip that or if you cancel that by accident, right, you're going to end up with something like very logically incorrect. Okay, so that's my bottom line. Okay, I really got to point out. Right? So don't go that way. Don't fall into that trap right there. And then sometimes you have, like say for example, the tangent, right? The tangent theta, by definition, we take the sine of theta and we divide that by cosine of theta. But then there were quarters in my past that I taught my student, and at some point when they were taking tests and exams and they got nervous and things like that, and they canceled it. So the tangent theta, they simplify that and they turn it down into just sine over cosine, and then this turns out to be completely meaningless. See what I mean? So don't do that, right? Don't do this kind of thing. Right? All right. So that's a remark I want to make sure you guys know. We learn how to prove a trig identity. Prove a trig identity. So let's look at proving a trig identity. Now I've explained this before, but now let's really get that nailed down with an identity in general. It doesn't have to be a trig identity. Just anytime working in math, you hear the term identity. An identity is basically an equality. Okay? An equality, sort of like an equal expression, right? This side is equal to the other side. An equality that is true for all values of the variable. And you may even have multiple variables. Then let me bring up a few little examples again of these examples just to point out what an identity is for you. You guys are familiar with the x squared minus y squared is famously equal to what? The product, right? Of x minus y times x plus y is this. Okay. So this is not a trig identity, but it is an identity. So what does it mean by being an identity? It was proven to be always true no matter what x value is and what the y value is. So for all values of the variables involved here, x can take equals 1, right? Y can equals 3. 1 squared minus 3 squared will always be equal to 1 minus 3 times in product with 1 plus 3. Right? And that's what an identity is. And so I'm bringing out something that you should have seen in your previous course before, right? And then we're going to step even forward into doing this. So that's what an identity is. Right? An identity is an equality. See, equality. Two expressions are claiming to be equal for all values of the variables. But now we want to pay even more attention into the trig identity. Right? The trig identity. So the one we've seen, we learned right here in this class earlier. Sine squared of theta, right? Plus cosine squared of theta. See, these are the variables, right? The angle theta is the variable. So for all angles, right, or for any angle value, what is this famously equal to? 1. So you have already seen another identity right here in our class. And that's this one specifically here is a trig identity. This one here was an identity, but it's not a trig identity. So in that way, here I'm going to take you guys through a few examples. And then each example points out a style of how we can prove. Okay? The point of proving is that we want to show as a generality of why it's always true. So let's look at example number 1 right here. We want to prove 1 plus cotangent of theta over cosecant of theta will always equal to sine of theta plus cosine of theta. There's the example I want to bring in. In this example, it's a proof we want, and then you can just make note of this. This is one style of proving for you. So the first example to show you one common style of how people can prove an identity out there, general. That's why, you can decide to write down style number 1, or if you want to skip that, that's completely fine, as long as you understand the intention of the example. So you have to understand, as a general picture of the problem right here, why are we doing a proving problem? Why do we need to do a proving problem? Because some people may make a claim that, hey, the left-hand side here, this expression on the left-hand side will always equal to the expression on the right-hand side. Doesn't matter which, for all values of the variable here, but that's just what people say, right? In order for you to believe, you gotta make sure, you gotta prove in the general case. You gotta make sure, and the point now is that we gotta do some math so that we are independent with picking examples. You don't want to substitute in theta equals pi over 2 to make sure the left-hand side equal the right-hand side. We don't want to try again for pi over 3 to make sure the left-hand side equal the right-hand side. Because going that way, we don't know how many times we have to pick examples to make sure it's true. Okay? So now we want to come up with a style to always ensure that the left-hand side will always equal the right-hand side, independently with examples that we pick. And that's the idea. Right? And so the style I'm about to show you here is very common style. We're going to start out with one side. We pick one side, right? And usually we pick the side that looks a little bit more complicated. So in this one right here, the left-hand side is a little bit more complicated. Are you understanding my word? Okay. We're starting out with picking one side. So what can we do with that one side? So I pointed out the reason why I chose the left-hand side, right? Simply because it looks more complicated slightly. So 1 plus cotangent theta over cosecant theta. I picked that side, simply one of the two sides, okay. But I purposely chose this one guy because it was a little more complicated. So the reason now is that we picked the more complicated side because we've learned that skill in the early lecture that we can simplify this, right? Let's go ahead and simplify this side right here. So now we're gonna apply the skills we've learned from the previous lecture, right? We already learned how to simplify. So first of all, to simplify this, 1 plus cotangent now can be rewritten as cosine of theta over sine of theta. You guys follow? And by saying simplifying, some of you may expect that, hey, this step will immediately need to look simpler. It doesn't necessarily have to yet, but we gotta keep working it out, and eventually we're gonna find some way to simplify it down. So right now, the best I can see is cotangent can be written as cosine of theta over sine of theta, right? And remember again, don't cancel out the theta, right? Always have to count. The cosecant is the same as a 1 over sine of theta. So for now, it seems like we even grew the expression to be a lot more complicated, but trust me, it will come, right? So, but once again, the big picture here is we want to start out with one side, and more commonly we pick the side that's a little more complicated, and then start working it out, right? And find a way to simplify that. So from that point, I'm going to get into, so in the next step, it's still equal, because it's now all valid, right? So that step right there we've had, so on the numerator I'll have, think about the 1 right there. 1 is, we can make the common denominator, so we can make that sine of theta over sine of theta. That's what happened to the first term 1 in the numerator. And then we can rewrite the other term, cosine of theta over sine of theta. So what I just did here is I was making common denominator between the two terms in my numerator. And then the denominator here, that big denominator fraction is still kept the same for now. Right? So now that term 1 is turned into a sine theta over sine theta. And I did that for that reason, to make it common denominator with the other term, that's all. And so now one more step further. I can now algebraically combine these two fractions into a sine of theta plus a cosine of theta over a sine of theta. And then the other one in the denominator, 1 over sine of theta. I combine the two fractions in my numerator of this bigger expression. All right. And then we can keep going, because every step right here, the simplification work is using it, understanding that everybody knows, right? That everybody's learned about that. And so now I'm going to rewrite the whole fraction here. See, there's a fraction in the numerator. I'm going to rewrite it as a sine of theta plus cosine of theta over sine of theta, but now dividing by that fraction in the denominator, I'm going to multiply by the reciprocal, right? So now we have a sine of theta over 1. All agree with the math, I guess, with the algebra. So now right there, what else can we take as action here? We can cancel out the sine of theta just fine, right? Now the whole sine of theta can be cancelled away, because that's one meaningful expression. Right? So I canceled out that sine of theta, so making it what? Sine of theta plus cosine of theta. So the point now is that, see, we simplify it down, and every step here we make viewers understand and follow well with every single thing we're using in here, right? And then we reduce that down to some expression that exactly equals the other side. So we're starting with one side, we're simplifying it down, right? We work it out through the algebra, using all the trick understanding we had, and then we land into the expression that exactly equals the right-hand side. And so now at that point, you can make your final conclusions, right? So therefore, it's a common habit that we write a final statement. The left-hand side that we started, 1 plus cotangent theta over cosecant theta. That expression must always, and see, in every step we were working here, none of these steps we had to bring in an example for theta. Right? We didn't have to use a theta equal pi over 4, theta equals a pi over 2, and none of that. And we were working with, hey, generally for any theta, right? It's always true with any of these simplification steps here. So now we're solidly firm that its left-hand side should equal sine of theta plus cosine of theta. Okay. That's how we have proven a trig identity. Okay. And so now, style number 1 that I was introducing, the most common style in improving a trig identity or improving an identity in general, is that we pick one side, right? And a little more commonly, the side that has more complicated set up for that. We're starting out with that, and we're simplifying it down and see if we can eventually land into an expression that exactly equals to the other side that we didn't pick. So now, this is just for you to know, but when you're writing a proof, right, this is a big, huge period indicating that's the end of our proof again. Right? Let's say we want to prove so yes, you can see that's why I brought in that earlier example just to point out that style you've learned is very common, right? We can all start out with something like that. So let's pick one side, right? And here kind of bring about it between these two. It's kind of hard to tell which side is more complicated. That's the first thing that caught your attention, right? See what I mean? Okay, so it's just me, I guess. I'm more comfortable with starting with the left side, right? But I'm not saying that the left side in this case is more complicated. Somebody may see that this one here is more complicated. Somebody agrees with me that the left side is more complicated. It's just something I picked as a choice here. So starting out similar to the earlier style that we've learned. So secant of theta minus cosine of theta. We want to simplify this down a little bit. Right? So here we're having what? The only thing we know about secant, because cosine is pretty dead end, right? Everything about cosine we already knew, and once it's written down as a cosine theta, it's pretty dead end. But this term right here, maybe there's something else we can rewrite about it. So secant of theta can be rewritten as a 1 over cosine of theta. You guys agree? Okay, so that's like everybody knows, right? And then the cosine, the minus cosine theta term remains exactly the same for now. So that's my next step right here. I brought in something that, see, anyone reading your paper when you write it like that, right? They gotta agree. Like, that person has to agree because everything is straightforward to the basic strict understanding. Okay? And now with a little more algebra, we can move on as the next step right here. You can write this as a, see, we can make a common denominator. So this cosine of theta is the same as over 1, right? That's a quick algebra work with this. I can make that as a 1 over cosine theta for the first term. But now minus. So here I'm going to both multiply top and bottom here by a cosine theta times another cosine theta, right? Then over cosine theta. I made common denominator. And then in my next step, I can combine the common denominator. I mean, I can put it all in one denominator. So cosine theta is the common denominator. Here I'm looking at 1 minus cosine squared of theta. So let's take a pause here, because somebody recognizes it, somebody may not. So we keep breaking it down, but at a certain point where we're not seeing clearly where to go next, right? That's a strategy right here. So far we stick with that plan like we've done in the earlier style. We started with one side, right? And the idea we started with one side, we keep working it out, but at some point it feels hopeless. You're not sure where you're going. You're not sure where you're going. We keep simplifying that. So here's what else you can do right here. So now I'm going to start out with, I'm going to leave it a pause again. I'm going to put a pause right here. But the right hand side on the other hand, right? On the other hand, this is what I can see right here. Sine of theta times tangent of the theta on the right hand side. So the style here starts splitting into a different route right there. You work somewhere far enough on the left hand side, and then now you're gonna turn your focus to the opposite side as well, to the other side as well. Okay? And then so sort of like we do both sides. On the other hand, sine of theta times tangent of theta, you can rewrite that as what? Sine of theta, pretty dead end, multiply with the sine of theta over cosine of theta. You guys following? So with this way of how you're rewriting it, nobody can argue with you on that, right? Nobody can disagree on that because it's well-known information. We're bringing just well-known information. And now what else can we do with this? We can rewrite that current step here from the right-hand side. On the right-hand side, we can rewrite that current step as a sine square of theta over cosine of theta. Are we good? And now, let me bring in another reminder for you. We have learned a few known identities. Sine square theta plus cosine square theta, right, equals 1. We've learned that one, right? there's no need to prove it again. We have learned that from that one we also have sine square of theta equals 1 minus cosine square of theta. You guys follow it? By subtracting that. And so right here from that left-hand side, right? And I'm talking about, see, here you're using some known identities right here. We can turn that into a 1 minus cosine square of theta equals a cosine of theta. Right? So now the idea here is that we work out at some point on the left-hand side, and then I'm talking about, if you think about in that scenario, that right when you were at that moment, you didn't remember to use some of these known identities right here. See what I mean? And then you can put a pause. You turn your focus to the other side, right? Rewrite it, and then all of a sudden, when you come to the sine square, maybe your mind at that point click with, hey, I remember that sine square is indeed equal to a 1 minus cosine square. I mean, you could have done that at that point, but I'm talking about in that situation where you didn't remember at that point, right? And then so you can work on the other side, and then at some point, right, if you remember sine square of theta equals 1 minus cosine, then now what do you see? Right-hand side turn into some expression, and left-hand side turn into the exact same expression after rewriting. See what I'm saying now? Left-hand side led to that expression. Right-hand side also led to that same expression. Okay? And so that now leads to, therefore, okay, our beginning expression, secant of theta minus cosine of theta must equal sine of theta times the tangent of theta. And that is the end of our proof right here. Right? So once again, the reason here, the argument here is simply because both left-hand side and right-hand side led to the exact same, right? Both came to an equal to that final expression, 1 minus cosine square over cosine theta. Okay? And then when it comes to proving, I'm showing you just different styles, as many styles as I know. And this style number 2 right here, the generality I want to show you guys is that you can sometimes work on both sides, right? Work on both sides independently, and then eventually both sides come to some expression that both agree, right? And so you can make that final conclusion. You can make that final conclusion that left-hand side will at the end equal the right-hand side. That's how we're proving it. You see the different way of how we're approaching it right now? But now, as I have pointed out, the different styles of doing this, you don't have to worry about which style do you have to go, okay? Because it's just like there's so many different directions. And so depending on your creativity, that you can just use strictly the style number 1 only, or sometimes you can make some creativity and stay with style number 2. Like say right here, that with this problem right here, see, I could have also, but that provided you gotta always remember all of your known identities, right? So from that point, you could have just gone one step further and making that the sine square over cosine, and then turn that into a sine over tangent, sine times tangent. There are many ways how you can. There are 2 different styles that you can always approach any one of the 2. Right? So the 2 examples we've done, these are, you have to understand, these are identity that's known to be true, that's already known to be true before us. And so that's why people are getting us here, just to see how you can prove it. See what I mean? Maybe think about it. When you are asked to prove an identity, the point is that it has already been true, but we want to make it, we want to convince ourselves of that. Okay? And then so that's a skill right there. But now I want to bring you guys into another one. So when it says prove, logically speaking, the equality will be true. It just, what matters is how you can make people convinced that it's true. But how about in an example like this? Now instead of proving, sometimes you may be asked to disprove. It's also another technique right here. How about sine of theta plus cosine of theta equals 1? And that's, when it comes to disproving, there's only one technique right here, and I'll show you guys. Think about something like this. All right, let's say x plus 2 equals 5. Okay. What I have in front of you is an equality, right? Is this true for all x values? Tell me that. Is this equality true for all x values? No, right? It may be true, but depending on some specific x value, it's not true for all x values. That's why something like this, when people write it on the board, it's only an equation to solve. That's why you have the solving problem, because you want to find that specific value or specific values, right, of the variable that makes the left-hand side equal to the right-hand side, but it's only an equation. It's not an identity. See what I mean? Okay. So when people is asking you something like this, and hey, is it true or not? You're gonna want to disprove. Okay. So how do you disprove something like this? You want to point out that hey, there are examples, there are values out there that the left-hand side fails to equal the right-hand side. So you can just disprove by left x, right, equals a 2 right here. See what I mean? So when x equals 2, the left-hand side gives you what? Left-hand side gives you a 2 for x plus 2, right? That answer comes out what? 4. But the right-hand side, right? On the other hand, it's a 5. Are these equal? Right? They're not equal. See what I mean? So the example that points out how this equality will fail right here, the example that points out how the equality fails, we call this one right here a counter example. See what I mean? Okay. So sometimes when you sense that hey, this equality people give you may not be true for all values of the variables, okay? Right? And we think about hey, let's disprove it. See what I'm saying? So disproving something, that means we're going to bring in maybe 1 or 2 counter examples. See what I mean? You got to also understand, bringing in counter example may be a little dangerous because maybe the first example you bring in, it may work. Let's say, for example, sometimes if you happen, because picking a value, an example for your variable, maybe who knows, first time you may pick 3, x equals 3. It will make the left-hand side equal to the right-hand side. So you may think that, hey, it's the truth. But no, it's only true for x equals 3, right? What about some other one? So picking counter examples, there could be times where you have to pick multiple counter examples. See what I mean? Okay. And so we're gonna bring that philosophy, that idea, that fundamental into this proving this trick identity right here. It's a claim to be, right? It's a claim to be, but then without it. Actually, now the real truth is that when a problem like this is asking you to disprove behind the scene, it shouldn't be true, but we've got to make it clear why it's not true. Okay? So, we're going to go by counter example. Let's say you guys want to pick a theta. So pi over 4, see, this is a value for your variable, right? We pick 1. So, into the expression, and you've learned all of these skills up to this point. You're going to evaluate sine of theta, so now it's sine of pi over 4, right? Plus cosine of theta, which is cosine of pi over 4. You guys follow it? Right. Will this come out equal 1? Okay. We put a question mark there, right? Will this come out equal 1? So let's go ahead and find that out even further. Sine of pi over 4, no. Root 2 over 2. That's right. And have your unit circle ready anytime we get into these simple calculation problems. What about cosine of pi over 4? Another root 2 over 2, right? There you go. We added these. We want to find out if that's equal 1, right? Will root 2 over 2 plus root 2 over 2 equals 1? Okay. We're still putting question mark, but so 1 is a pretty well-known number, but what about root 2 over 2 plus root 2 over 2? It makes it 2 root 2 over 2, right? Will that equal 1? Putting question mark there, right? The 2 on the left-hand side cancel. That leads to square root of 2 equals 1. Is this true? What's the value for square root of 2? The actual value for square root of 2 is 1.4 something, right? 1.414 or something like that. So now at this point it's all clear. It's so clear that the square root of 2 over 2 is not equals 1. So this one counter example already is everything that needs to say that we have disproved this, right? This cannot be true here because that's that value of the variable theta where the left-hand side failed to equal the right-hand side. See what I mean? Right. So in that way I'm saying that I have disproved, right? So therefore, general sine of theta. Just saying general means for all values, then sine of theta plus cosine of theta is not necessarily equal to 1. Okay? It's not always equal to 1. Yeah? So we have just disproved it. So I brought in this example for everybody to understand that this example is still an elementary example in a sense that it already led you into one direction. It told you, it let you know that the equality here is not true. But how do you make it clear to people that it's not true? That's why we're disproving it. Okay? The intention here is it's already not true. And then we've got to bring it out clear by bringing up counter examples of why it's not true. Okay? So the first two examples, you've learned the two sides of that you can prove it, some equality being always true. Okay? Here we learn how to disprove it. Some equality is already known to be not true, but we got to learn how to make it clear to readers, to viewers that it's not true. Now let me bring in the third one. The next kind here. The third kind of problem. We're putting that in example 4. Example, let's say the wording instruction says, let's determine. We want to determine whether the equality. Equality, how about the first equality right here? Part A. Cosine square of theta minus sine square of theta equals 1. So we want to decide whether that is true. Okay. Or false. That's where it is. This is where you have two different directions that may happen, two possibilities that may happen with your equality. That may be false, and that may be true. Okay. Here's how brain process works here. You guys ready? See, like I said, this equality people giving you now, they don't know anything about it, and they're asking us to find out. We got to find out, is it true or is it not true? See what I'm saying now? So there's two things for us, and the experience here is kind of like a combined experience. See, if you suspect that it's not true, then you bring in counter examples, right? If you suspect that it's true, then you're gonna have to prove it. So the proving skill is like what we've done in example 1 and 2. But then if you, like I said again, if you are suspecting that it's not true, right, then you're gonna have to use the disproving skill by bringing in counter examples. Right? But then now. Real experience, real-time experience is applied right here. Let me tell you, a lot of times, let's try to bring in counter examples first. Because if it's not true, then a couple counter examples is going to show us that it's not true. Okay? So let's just bring in counter examples. Okay. Any possible counter examples? Well, think about theta equals pi over 4, like you guys chosen earlier. Choosing your variable being pi over 4, right? And you got cosine square of pi over 4, agree? The left hand side minus sine square of the pi over 4, right? Will this equal 1? Well, what's cosine of pi over 4 again? 2 over 2, but our expression is asking for the square of that, right? So the square of 2 over 2, we want to minus, what's sine of pi over 4? The expression here is asking us to square that, right? Square root 2 over 2 or square minus square root 2 over 2 or square. What's the overall? It's a 0, right? The exact same term, right? Cancel out each other. It's a 0. So now what do you see? Does that equal the right hand side? It doesn't, right? So right here, one counter example is good enough. So now what do you decide? This equality here is false. See what I'm saying now? So the logical step here is let's bring in the counter examples first. Maybe some example it works, but let's not rush. Find another counter example and find counter example. And then if it's not true, it's among your counterexamples, it will fall out and making some conflict. So this expression on the left-hand side evaluated at theta equals pi over 4. That expression on the left-hand side will equal 0, which is definitely not equal 1. Right? That's why this equality here fails. Already, it's not because it's not true for all theta. Right? So it cannot be an identity. So just now we have disproved that. But let me bring in another one, still in the same kind of problem. Let's call it part B. So we still want to determine whether the statement given, the equality given can be a true identity or a false one right here. Okay. So how about cosine squared of theta minus sine squared of theta equals 2 cosine squared of theta minus 1. We want to determine that. So like I said, we don't know if it's true or it's false. Okay? True or false, right? We want to determine that. So I'm continuing the wording instruction right there. Determine whether that's given one, right, is true or false. So the logical steps again. Let's try with all the with as many counter examples as we can. Okay. Theta equals pi over 4. What do we have? Okay. Left hand side gives me cosine squared over pi over 4 minus a sine square over pi over 4, right? That's the left hand side. And that comes out with 2 over 2 all squared for the cosine square minus with 2 over 2 all squared for the sine square, and that equals 0 as you already knew, right? But for this specific counter example, the right hand side 2 cosine squared pi over 4, because right now we're letting theta equals pi over 4, right? So the right hand side 2 times cosine squared right there minus 1. What will that equal to? 2 times, as the expression set up, multiply with square root of 2 over 2 all squared, right? And then minus 1. What will this equal? Well, you can see that that's here, it's going to go 1/2, right? Square 2 over 2 all squared is 1/2. You guys agree? Okay. And you can check with the algebra. Sometimes outside of the lecture here, and we can subtract 1. And then 2 cancel with that 2 right here is giving me a 1 with minus 1. It's also a 0. So with this first example right here, right, it's already true. But then we cannot go from by simply picking one example and then say, hey, it's true, right? Because when saying true, that means it's true for all theta that you can choose. But we have only chosen one, and maybe we're lucky that it worked, but who knows? Picking another example is going to fail. So we're going to have to try again. We'll pick another example. Right. So these are, for now, we're currently relying on the examples. So left-hand side, okay? Left-hand side gives me cosine square of the pi over 3. More practice for everyone. What's cosine square of pi over 3? Okay. 1/2. That's right. But don't forget, 1/2 all squared, right? Cosine of pi over 3 is a 1/2, but now cosine squared gives me 1/2 all squared. Right? What's sine of pi over 3? Root 3 over 2, I agree, right? Now, but the expression here on the left-hand side says sine squared, right, of root 3 over 2, of pi over 3. So from there, we got root 3 over 2, all squared. Subtracting out these two expressions. So that 1/2 all squared gives me a 1/4. This one here is a 3 over 4, right? So the left-hand side will come out with the evaluated value being negative 1/2. You guys good with me on that? The right-hand side, on the other hand, 2 times cosine square of pi over 3. Again, because I said in this current quick little example, right? I use theta equals pi over 3. So right-hand side, 2 cosine square of the angle minus 1, right? Because that's what the right-hand side is. So what do I see here? 2 times, right? 1/2 r squared minus 1. Because cosine of pi over 3 is once again 1/2, right? And that's making it 2 times the 1/4 minus 1, making it another. So 2 cancel with the 4 in the denominator, making the first term here being a 1/2, right? And then minus 1 right here. It gives me another 1/2. So we found another example where the two sides are still equal, right? See what I'm saying now? And then you guys can spend your time finding out some more. You can go with theta equals a pi over, pi over 6. It's also going to work in any other angle. So now after a few examples still successful, after a few successful examples, we don't want to hopeless. We keep putting in more examples because there will be never enough examples to put in. See what I mean? Now we're going to start proving it formally. Okay? So now thinking about proving it formally, because we've done quite a few attempts and they're all true. So now we need to prove in the more general cases right here. So now we're having quite a little bit of a problem about that. It's true, and we're going to say, see, I could just easily use a style number 1 right there. 2 cosine squared of theta minus 1 right there. That one right here in my next step. Here's how I'm seeing it. The first term 2 minus cosine squared theta, okay, I can keep it the same. Okay, keep it the same with minus. Now the 1 right here is famously equals to what? Sine squared theta plus cosine squared theta. Right? It's a little while, but you guys think about it, and ever since we learned that famous Pythagorean identity, right? Start putting it somewhere in your mind and keep bringing it back. Okay. Anytime you see a 1, think of that in the back of your mind. 1 will always equal sine squared plus cosine squared. Right. And then minus 1 means here I put the sine squared plus cosine squared in parentheses, and then that name sign will eventually change the sign for each of my expressions. So here I'm looking at what? That equals 2 cosine squared theta plus some stay the same minus sine squared of theta minus another minus cosine squared of theta. And now do we have like terms? See, 2 cosine squared, right? Minus cosine squared. That gives me the cosine squared of theta minus sine squared. If we land into something that generally equals exactly the other side. Yeah. Okay. Now, after trying a few examples, right, we affirm that it may be true. We highly suspect that, right? And then now we formally proving it for the general occasion and for all the values of theta. So now we can make it. That's right. Therefore, cosine squared of theta minus sine squared of theta equals 2 cosine squared theta minus 1. Right? And that's true, right? See what I mean? And also just proving it